Yes, good morning. It is now 5 minutes past 11. We cannot wait anymore. Let's start our class. And in the previous class, we started to study about drawing the Lewis structure of molecules. When drawing the Lewis structure of a molecule, we follow three basic rules. The first rule we should follow when drawing the Lewis structure of a molecule is to involve only the valence electrons. So involve only the valence electrons, because during the course of a chemical reaction, it is only the valence electrons that are involved. The core electrons, the neutrons and the protons are not involved. Only the valence electrons are shared when a covalent molecule is formed. So when drawing the Lewis structure, we only worry about the valence electrons, the ones that are involved in chemical bonding. And then we share these valence electrons among the elements that are involved in chemical bonding. Then when we are doing that, we must follow the octet rule. If we have elements in the second row of the periodic table, like carbon, nitrogen, oxygen, fluorine, and also the halogens, if they are involved in covalent bonding with other elements, we must make sure these elements are surrounded by 8 electrons. The octet rule must be followed. Then if the element that is involved in chemical bonding is hydrogen, we must make sure the duet rule is followed. These are the rules we should follow when writing the Lewis structure of organic molecules. So let me just start by revising what we have looked at in the previous lecture, the drawing the structure of hydrogen fluoride, HF. So this HF is a covalent molecule that has got a covalent bond between hydrogen and fluorine. During the formation of this covalent bond between hydrogen and fluorine, one electron from hydrogen and another electron from fluorine are shared in the formation of the covalent bond in HF. And then the electrons that are involved are the valence electron. And then if you look at hydrogen, hydrogen has got one electron in its valence shell, while fluorine, being a halogen, has got 7 electrons in its valence shell. So these are the electrons that we should worry about. You remember the first rule when drawing the Lewis structure of a molecule says, consider only the valence electrons, nothing else, only the valence electrons are involved. So in HF, you have hydrogen, which has got 1 valence electron, and fluorine, which has got 7 electrons. So the total number of valence electrons in the molecule hydrogen fluoride are 1 plus 7, 8. And then we share these 8 electrons between the hydrogen and fluorine, following the octet rule as well as the duet rule for hydrogen. So first, in this case, we can draw the Lewis structure for hydrogen and fluorine, okay? For hydrogen, its Lewis structure is where you have the symbol hydrogen with 1 electron. This is the Lewis structure for hydrogen. And then for fluorine, the Lewis structure is as shown here. We have the symbol for fluorine, and then the 7 valence electrons of fluorine. You remember, electrons, as much as possible, they should be paired. So since we have 7 electrons, in these 7 electrons, 3 of them are paired. So we have one pair, and another pair. 3 lone pair of electrons, and then the 7th electron as 1 electron in here. So when you are drawing the Lewis structure for hydrogen fluoride, since this molecule exists, it exists because there is a chemical bonding between hydrogen and fluorine. And then this chemical bonding between hydrogen and fluorine is formed as a result of sharing of 1 electron from the hydrogen and 1 electron from the fluorine. So you bring 1 electron from the hydrogen and 1 electron from fluorine to form the covalent bond. So both hydrogen and fluorine will donate 1 electron to form a 2 electron bond. So this bond will form. So when you look at this bond, you'll see that it has followed the octet rule as well as the duet rule. The duet rule applies only for hydrogen, while the octet rule applies for the other elements of period 2 of the periodic table, including all the halogens. So if you look at the hydrogen, you have these 2 electrons shown in blue. These are the shared electrons. These shared electrons are between the hydrogen and fluorine. They belong to both hydrogen and fluorine. So you can easily see that on the hydrogen, we have 2 electrons following the duet rule. The hydrogen has 2 electrons, just like the corresponding noble gas helium. Then when you look at fluorine, you will see that the 2 electrons that are shown in blue are the shared electron, the electrons that form the covalent bond between the hydrogen and fluorine. Those ones are counted as shared electron. So we have these 2 electrons, and then we have the 6 electrons that are shown in red. So the total number of electrons around the fluorine are 8. So both the duet rule as well as the octet rule is followed when this molecule of hydrogen fluoride is formed. When the Lewis structure of HF is written, 1, we only used the valence electrons. 1 valence electron from hydrogen, 7 valence electron from fluorine, a total of 8 electrons. That's 1. The other rule we followed, the octet rule. Around the fluorine, we have 8 electrons. We also followed the duet rule. Around the hydrogen, we have 2 electrons. Of course, chemical bond between 2 elements is represented by a solid line. So in this particular case, we have 2 electrons around, 8 electrons around. Anyway, this solid line represents a single bond between the hydrogen and fluorine. This solid line represents 2 electrons. So if you have 1 solid line, that solid line will represent 2 electrons. If you have 2 solid lines, that's a double bond, represent 4 electrons. If you have 3 solid lines between atoms, that represent a triple bond, then each of the solid line are as a result of sharing of 2 electrons. As a result, 3 solid line represent 6 electrons. I don't want you to forget that, okay? A line represent 2 electrons. So when you are counting the electrons around the hydrogen, you'll say 1, 2, because of this solid line, which has got 2. And then when you count for the fluorine, you'll say 1, 2, the solid line, then 3, 4, 5, 6, 7, 8. Now, when this molecule of HF is formed, the 8 valence electrons of the hydrogen and the fluorine are found on this molecule HF in two different ways. One way in which the electrons exist is as shared electrons, the ones that are between the hydrogen and the fluorine. The ones that are involved in chemical bonding, these ones are called shared electrons or bonding electrons. But if you look at these three lone pair of electrons, these are not shared electrons. They are only on the fluorine. They are not used in the formation of a chemical bond between the fluorine and the hydrogen. So these ones are unshared electrons or non-bonding electrons because they are not formed in chemical bonding. So they are called unshared because they are not shared. They are called non-bonding because they are not involved in chemical bonding. So these three electrons are called non-bonding these three pairs of electrons are called non-bonding electrons, unshared electrons, or simply lone pair of electrons. So on the fluorine, we have 1, 2, 3 lone pair of electrons. What you should know, the electrons, when they are found on elements like this, they exist as a pair. So this solid line represents a 2-electron bond, and then these 3 lone pair of electrons, the unshared electrons, are the ones that only found on fluorine. So when you are counting the number of electrons on the fluorine, you will count 1, 2, 3, 4, 5, 6, 7, 8. Sometimes, and most of the time, when you write the Lewis structure, when we write the structure of hydrogen fluoride, even in books, you will find the structure, the Lewis structure for hydrogen fluoride written simply as HF, like this. We are not indicating the 3 lone pair of electrons, but you should know those 3 lone pair of electrons exist on the fluorine. The same when we are writing the structure for water, we just write H2O. But you should remember, on the oxygen of H2O, we have 2 lone pair of electrons. When we write the structure for ammonia, when we write the Lewis structure for ammonia, we just write NH3. But we should not forget, on the nitrogen of ammonia, we have 1 lone pair of electron. But when you are drawing the Lewis structure in this unit, okay, you have to indicate the lone pair of electrons. Without indicating the lone pair of electrons, the Lewis structure will not be complete and will not be acceptable. Okay, so the resulting molecule, this one, gives both hydrogen and fluorine a filled valence shell. For hydrogen to have a filled valence shell, it requires 2 electrons. For fluorine to have a filled valence shell, it requires 8. So this gives the hydrogen 2 electrons and the fluorine 8 electrons. Is it okay? Do you have any question on this? Omar, you have raised your hand. Do you have any question?
No, I'm good.
Okay, so as a result, you have to lower your hand, okay? Because when you are raising your hand, it means you have some query. Isn't it true? Like if it is in a class, if you raise your hand, I cannot ignore you, isn't it? It's the same, that's how I feel on this. Okay? But do you have any question, any of you, on what I have discussed today in the previous class? Is it clear?
Yes.
Okay, so let's continue.
Yeah, it's clear.
Okay, so as I told you, when you are drawing the Lewis structure of a molecule, a solid line indicates a 2-electron covalent bond. Just a line represents 2 electrons. You'll count a solid line as 2 electrons. If you have 2 solid lines, those are 4 electrons. If you have 3 solid lines, those are 6 electrons, because a single solid line indicates a 2-electron covalent bond. Now, from what I have discussed with you, that the number of a covalent bond a particular atom will form is dependent on the number of additional electrons it will require to have the electron configuration of the corresponding noble gas. For example, hydrogen forms one bond. The reason why hydrogen bonds form only one bond is because hydrogen will want to have the electron configuration of the corresponding noble gas helium. Helium has got 2 electrons, okay? But hydrogen has 1. To have like that of helium, it requires an additional 1 electron. As a result, hydrogen forms one bond. You cannot have a hydrogen bonded on this side, on that side, on that side, on that side. It only forms one bond. Like if you look at the molecule of methane, where you have 4 hydrogens, you will see all these 4 hydrogens have formed a single bond with the carbon. Okay, hydrogen forms only one bond. And then if you look at carbon, carbon has got 4 valence electrons. It is in group 4A of the periodic table. As a result, carbon will need additional 4 electrons to have the electron configuration of the corresponding noble gas neon, additional 4 electrons. So as a result, carbon forms 4 bonds, as in the case of methane, for example, CH4, where the carbon has formed 4 bonds with the 4 hydrogens. Of course, when it forms these 4 bonds, it does not have to be single bond, okay? It can be a double bond, it can be a triple bond. But when you count the number of bonds it has formed, you'll find there are 4. Then if you look at nitrogen, nitrogen is in group 5 of the periodic table. It has got 5 valence electrons. So when nitrogen forms a bond with other elements, it will form 3 bonds because it only needs additional 3 electrons to have, together with the 5 valence electrons it has, to have 8 electrons. So nitrogen forms 3 bonds. So hydrogen forms 1 bond, carbon forms 4 bonds, it is tetravalent. Nitrogen forms 3 bonds, it is trivalent. Then oxygen has 6 electrons in its valence shell. It requires additional 2 electrons to have 8. So oxygen forms 2 bonds, as in the case of molecule of water, H2O, where you have the oxygen forming two bonds with hydrogen, 2 single bonds with hydrogen. Oxygen is divalent. Then if you look at the halogens, fluorine, chlorine, bromine, and iodine, these halogens, these ones have got 7 electrons in their valence shell. To have octet of electrons, they need 1 additional electron. That's why the halogens form 1 bond, just like the hydrogen. Okay? So for example, you have a molecule of chlorine, where you have a chemical bond between one chlorine and another chlorine. You have a molecule of hydrogen fluoride, where is a single bond between hydrogen and fluorine, 1 bond. A molecule of HCl, hydrochloric acid, where you have 1 bond between hydrogen and chlorine. So these are the number of bonds particular elements form. And this you must recognize, because when you are drawing the Lewis structure, for example, of an organic molecule that has got carbon, we cannot have a carbon that is bonded to 5 elements, 6 elements. Carbon that has formed 5 bonds. Carbon that has formed 6 or 7, 8 bonds. Carbon can only form 4 bonds. Now, if you look at hydrogen and carbon, hydrogen forms 1 bond. Then as a result of this bond, it will have the 2 electrons it needs to have the duet of electrons, just like that of helium. So on the hydrogen, we do not have any additional electrons. Then if you look at carbon, carbon forms 4 bonds. Each of these bonds are as a result of 2 electrons. 4 times 2, 8 electrons. So we do not see any additional electrons on the carbon other than the ones that are involved in chemical bonding with other elements. Now, when you go to the nitrogen, nitrogen forms 3 bonds. These 3 bonds will bring how many electrons? 6. Because a bond, which is represented by a solid line, is a 2 electron covalent bond. 3 times 2, 6. But nitrogen must have 8 electrons. It has 2 additional electrons, and then those 2 additional electrons appear as a lone pair. So when you are writing the Lewis structure of a nitrogen containing compound, you must show that the nitrogen has formed 3 bonds with other elements. And then on the nitrogen, we have 1 pair of electrons. Then when you look at oxygen, oxygen forms 2 bonds. 2 times 2, 4 electrons. It needs additional 4 electrons. Those additional 4 electrons are lone pair of electrons, which you find on the oxygen. This lone pair of electrons on the nitrogen, and then these 2 lone pair of electrons on the oxygen, they are not involved in any chemical bonding. These are the non-bonding electrons, the lone pair of electrons, the unshared electrons. Then when you look at the halogens form 1 bond. Of course, as a result of this 1 bond, they will have 2 electrons. But halogens, they must follow the octet rule. So they need additional 6 electrons. These additional electrons are the lone pair of electrons you find on the halogens. So these 3 lone pair of electrons will bring 6 electrons plus 2 as a result of the 1 bond, you'll have 8 electrons. So when elements are involved in chemical bonding, some of their valence electrons will be used as bonding or shared electrons, while the others will be used as non-bonding or unshared or simply as lone pair of electrons. And this you must know when you are drawing the Lewis structure of molecules. Okay, so this is just simple concept, nothing complicated. Okay, so this you must follow as we draw the Lewis structure. So now we'll just revise. Of course, again, I think it's a revision for you. We'll go through the steps of drawing a Lewis structure. The rules to be followed, the laws to be followed are 3 as I have indicated to you. 1, only involve valence electrons. 2, the octet rule must be followed. If it is hydrogen, the duet rule must be followed. These are the rules. So, however, to make our life easy, when drawing the Lewis structure, we follow steps, logical steps. So the first step is to arrange atoms. You arrange the atoms next to each other in the way you think they are bonded together. So for example, if it was HF, as we have seen, the hydrogen and the fluorine are next to each other. Very simple. If it is a molecule of methane that has got 1 carbon and 4 hydrogens, and then we have to determine how the atoms are arranged. Which atom is next to which one? Do we have hydrogen and then another hydrogen? So you have 1 hydrogen here. Next to that hydrogen, we have another hydrogen. Next to that hydrogen, we have another hydrogen. Next to that, we have another hydrogen. Next to that, we have another hydrogen. And then finally, we have the carbon attached to the last hydrogen. Or is it where you have the carbon in the middle and surrounded by 4 hydrogens? We must decide on how the atoms are arranged. Okay. Now, this is not an easy thing to do. Please mute your mic. Who is this who's put the mic on? Brian, your mic was on, just put it off, okay? So we arrange the atoms next to each other in the way you think they are bonded together, okay? So this is not an easy task as we continue, as we shall see as we go along. Sometimes you might have 3-4 elements that are involved in chemical bonding. For example, sulfuric acid. In sulfuric acid, we have 2 hydrogens, 1 sulfur, and 4 oxygen. When you arrange these atoms, which one should be at the center so that the others surround it? When you have such a situation, you put the least electronegative atom at the center. Between sulfur and oxygen, sulfur has a lower electronegativity than oxygen, so sulfur will be at the center when you are drawing the Lewis structure for sulfuric acid. Okay, so the first step is you arrange the atoms. And then as you arrange the atoms next to each other, you'll be guided by simple basic principle. One of the basic principles from what we have studied in the previous slide is that the fact that hydrogen forms only 1 bond. And the halogens also form 1 bond. Okay, so as a result, a hydrogen cannot be in the middle, or a halogen cannot be in the middle surrounded by other atoms with the possibility of forming a bond with them. So when you have hydrogens or halogens, you must keep these hydrogens and fluorines, hydrogens and halogens on the outside. So always place hydrogen and halogen atoms on the outside. The reason why we are doing that is because hydrogen and the halogens form only 1 bond. So you cannot put them in the middle. They must be outside, on the outside. So for example, if you are to draw the Lewis structure of the simplest organic molecule, methane, CH4, in CH4 we have 4 hydrogens and 1 carbon. So these 4 hydrogens, they must be on the outside with the carbon being in the middle. So this is how they should be arranged. The hydrogen are on the outside. The reason why we are putting them, the hydrogens, on the outside is so that they can only form 1 bond. So this hydrogen can only form a bond with this carbon. This hydrogen can only form a bond with this carbon. This one can form a bond with this carbon. Only possibility of forming 1 bond. So the first thing,
Yes. Your slide is not moving, sir.
It is moving. It is not on slide 100. Hello? Anyone who's seeing slide 100?
Yes, sir, it's there.
Yeah, because it delays because of poor connections, okay? So please mute back, mute, okay? Mute, and so we cannot have a situation where hydrogen can be in the center, in the middle. If you put the hydrogen in the middle, as in this case, you can see this hydrogen, the one we put here, can form a bond with this other hydrogen and also with this carbon. It will have a possibility of forming 2 bonds. Then each of these, hello? Brian, do you have a question? So should I mute everybody because of the disturbance of one rogue student? Lydia, why are you not putting your mic on mute? Unless you have a question, mute. Okay, let me mute everybody so that you don't have a possibility of talking to me at all. And if that's what you want, so you have it, okay? But it's not my choice, it's not my wish to mute everyone. It will be nice if you can communicate with each other, but I can't allow the class to be disturbed. So I've muted all of you. So if you look at this hydrogen, on this side, it can form a single bond. On this other side, it can also form a single bond, giving this hydrogen 4 electrons. But hydrogen can only have 2 electrons. So what it means, hydrogen cannot be at the center. Hydrogen can only be on the outside. So that's what you need to determine first. You arrange the atoms next to each other in the way you think they are bonded. So when you are doing that, we follow some very basic common sense from the chemistry we know from high school as well as at the university here. Hydrogen and halogens can only form one bond. As a result, they cannot be in the middle. They can only be on the outside. And then the other thing, when you are arranging these atoms next to each other, as a first approximation, as you start, you should not put more atoms around a particular atom than the number of bonds it usually forms. For example, if you have a carbon, we know carbon forms 4 bonds. If you have a nitrogen, we know nitrogen forms 3 bonds. If you have an oxygen, we know oxygen forms 2 bonds. So when you surround the atom, you should not surround it by atoms more than the number of bonds it usually forms. If it's a carbon, surround it by 4. If it is a nitrogen, surround it by 3. If it is an oxygen, surround it by 2. So this just as a first approximation, you do that. Okay, for example, if you are asked to draw the Lewis structure of the molecule with a molecular formula of CH5N, 1 carbon, 5 hydrogens, and 1 nitrogen, CH5N. When you draw the Lewis structure of this, you see that you have carbon, you have nitrogen, and also hydrogen. Even hydrogen should be on the outside. That means hydrogen should not be surrounded by more than 1 atom. So we keep the hydrogen on the outside. And then you will be surrounding the carbon and the nitrogen with other atoms. When you are surrounding them with other atoms, you should make sure, as a first approximation, the carbon should only be surrounded by, similarly, by 3 atoms, because nitrogen forms 3 bonds. So when you do that, you put the hydrogens on the outside, the carbon surrounded by 4 atoms, the 3 hydrogens you see, and the nitrogen. Then the nitrogen surrounded by 3 atoms, these 2 hydrogens, and the other carbon. This is what you should do as a first approximation. 4 atoms around the carbon and 3 atoms around the nitrogen. You will not, as a first approximation, do something like this, which will put 4 atoms around the nitrogen. The 3 hydrogens, 1, 2, 3, and 4. I'm not saying it cannot happen at all. But as a first approximation, when you try to figure out how the atoms are arranged, the first thing you need to try is to surround the atoms by no more than the number of bonds they usually form. So if it's carbon, it's surrounded by 4. If it's nitrogen, surrounded by 3. It is possible you can have nitrogen surrounded by 4. It's possible, like ammonium ion, which you have learned in high school, is NH4+, where the nitrogen is surrounded by 4 hydrogens. It is also possible you can have an atom surrounded by less than the number of atoms that are less than the number of bonds it usually forms. So this one is just as a first approximation. You try this and see if it works. If it doesn't work, you change situation until you are satisfied. Okay? So the first rule is about the arrangement of the atoms. You arrange them in the way you think they are bonded together. After you have arranged them, now you have to start forming a bond with them, okay? Of course, to form a bond, you'll be using electrons. Then the electrons you use are the valence electrons. So in the second step, you will count the number of valence electron for each of the atoms in the molecule. If it is methane, for example, CH4, in methane, we have 1 carbon and 4 hydrogens. Carbon has got 4 valence electrons, 4. Hydrogen has got 1 valence electron, but we have 4 hydrogens in methane. So 4 times 1, 4 electrons for the 4 hydrogens, plus the 4 electrons of methane, of carbon, giving methane a total number of 8 valence electrons, which it can use in forming a bond. So first thing you have to do is count the number of valence electrons for each of the atoms in that particular molecule. And then to determine what the valence electron, the number of valence electrons of a particular atom, you'll use their position in the periodic table. If they are group 1, 1 valence electrons. If they are group 2, 2 valence electrons. If they are group 3, 3 valence electrons. If they are group 4A, like carbon, 4 valence electrons. 5, group 5, 5 valence electrons. If it's nitrogen, if it is phosphorus, those are 5 electrons. If it is oxygen, if it is sulfur, those are 6 electrons. If it is halogens, it is 7. So from the position of the element in the periodic table, you determine what its valence electrons are. Okay? Now it is possible you can have a molecule that is ionic, either positively charged or negatively charged. It becomes negatively charged because it has gained electrons. The molecule becomes positively charged because it has lost electron. So if the molecule is negatively charged, it is negatively charged because it has gained electrons. As a result, when you are counting the valence electrons, after you have counted the valence electrons added up for all the elements, you have to add for each of the negative charge, because that will be the total electrons of that particular molecule. So if it is -1, you will add 1. If it is -2, you will add 2. If it is -3, you will add 3. For example, you can have a nitrate ion, NO3 minus. It is negative because it has gained electron. So after counting the valence electron, the nitrogen and the 3 oxygens on that one, you'll add 1. If it is SO4 minus sulfate ion, you count the valence electron of the sulfur and also the 4 oxygen, you add those together. On that one, you add 2. Because the sulfate became -2, the charge on the sulfur became -2 because it has gained 2 electrons. But if it is positively charged, it is positive because it has lost electron. So from the total valence electrons which you have added, you subtract. Subtract 1 electron for each positive charge. If it is +1, -1. If it is +2, it's -2. If it is +3, -3, etc. Then after that, the total sum of this will give you the total number of electrons that must be used in drawing the Lewis structure. Now, in step 1, we determine how the atoms are arranged. In step 2, we added up all the electrons, the valence electrons of the various elements that are involved in chemical bonding. If it is negatively charged, we added. If it is positively charged, we subtracted. Now we have the total valence electrons. Now we have to use, remember, in step 1, we have determined which one is next to which one. In step 2, we know how many valence electrons there are, which we can put on these atoms, the atoms we have arranged in step 1, following the octet rule and the duet rule. Okay, so the next step is arrange the electrons around the atoms. So the first thing you have to do is you have to form a bond between the atoms that are arranged, a single bond. So what you do, you place a bond between every two atoms in that particular molecule. You have to form a single bond first. So when you form this, when you add these electrons, of course, you follow the simple concept we have talked about. If it is hydrogen, you should not have more than 2 electrons. 2 electrons around each hydrogen. Then if there are second row atoms like carbon, nitrogen, oxygen, etc., which follow the octet rule, we should not have more than 8 electrons around this. So the first thing we do is we put a bond between them. Of course, a bond is 2 electrons. A line, a solid line, is as a result of sharing of 2 electrons. So you just put a bond, a line between the atoms that you have arranged because they have formed a molecule. So there must be a shared electron. So you arrange like that. That's what you do first. Of course, after you have done that, if you are left with electrons, you remember we have the total valence electrons we have counted in step 2. When you are putting these electrons, you are just sharing those electrons you have among the elements that are involved in chemical bonding. It is possible after you have formed a bond between the elements, you will be left with nothing. You will have used all of them in forming a chemical bond. It's also possible after you have put the single bond, you might be left with some electrons. Remember, we have to use all the valence electrons when forming that particular molecule. And then these additional electrons, you will put them as lone pair of electrons. Use all the remaining electrons to fill the octet of the elements that do not have octet of electrons. Then you put these electrons as lone pair of electrons. Okay? So first you form a single bond. After you have formed a single bond, you count the total number of electrons you have used in the single bond. If there is a balance from the total number of valence electrons which you have determined in step 2, those electrons you will give to the elements in that molecule whose octet of electrons is not fulfilled. You will give them these additional electrons as lone pair so that the elements will have octet of electrons. Then, even after that, if you see some of the elements do not have octet of electrons, now you'll use this lone pair of electrons as bonding electrons. You'll use those lone pair of electrons and use them to form a double bond or a triple bond until all the elements in that particular molecule have octet of electrons if they are second row element, or duet of electron if it is hydrogen. Then after you have done that, it is possible, as I told you, the element could be ionic. It could be positively charged or it could be negatively charged. So the step 4 is to assign formal charge to all the atoms involved in the chemical bonding. Okay, so for example, you have sulfate ion SO4 2-. The charge on the sulfate is -2. When you assign formal charge, you will be determining the charge on the sulfur and the charge on the oxygen to determine which of the elements in this ion contributed to the -2 charge. So you have to determine the charge on each of the atoms. You have to assign formal charge to all the atoms. When you have done all this, you will have drawn a very valid Lewis structure for a molecule. Remember what I've been telling you all along, that structure determines property. So you must draw the structure of the molecule very well. If it has got a lone pair of electrons, you must indicate. If it has got a double bond, you must indicate. If it has got a triple bond, you have to indicate, etc. And then it is this structure which is going to determine whatever property this chemical compound is going to have. So let's have some example. Let's draw a Lewis structure for methane, CH4, for example. So we have 1 carbon and 4 hydrogen. Step 1, arrange the atoms. So when you are arranging the atoms, we follow what I've told you. That hydrogen should be on the outside. Carbon will be in the middle. So you'll place carbon in the center and surround it by the 4 hydrogens. And these 4 hydrogens will be on the outside. This is the step 1. Step 2 is count the valence electrons. Now we have 4 hydrogens and 1 carbon. Hydrogen has got 1 valence electron. Carbon has got 4 valence electron because carbon is in group 4A of the periodic table. So we have 4 hydrogens, each of them having 1 valence electron. So the total number of valence electrons contributed by the 4 hydrogens, therefore, is 4 electrons. Then we have carbon, which has got 4. So therefore, the total number of valence electrons of the molecule of methane is 8 electrons. Okay, 4 electrons coming from 1 carbon and 4 electrons coming from the 4 hydrogens, each of them contributing 1. So this is the total number of valence electrons. Now we'll use these electrons in forming a bond in here between the hydrogen and the carbon. So now we have carbon forming a bond with this hydrogen, with that hydrogen, with that hydrogen, with that hydrogen. We'll use these 8 electrons first and foremost to form a bond. So add these electrons as bonding and lone pair of electrons, as bonds and lone pairs of electrons. So we have this molecule, this arrangement of atoms we have determined in step 1. So what you do first is form a single bond here, single bond here, single bond here, a single bond here. Add a bond between each of the carbon and hydrogen like that. So we have formed a bond. You cannot have a molecule where you have not formed a bond between the carbon, one of the carbon and the hydrogen. That's not a molecule. This is a molecule because they are formed bonds with each other. So we must form a bond. That's what we do first. Now, how many electrons did you have first? How many valence electrons we had first? We had 8 valence electrons. Then it is these valence electrons which we are going to use first to form a bond. After you have formed a bond, the first thing you need to do is to determine if each of the elements, no, even before that, you have to determine if we have used all the 8 electrons, all the valence electrons, which we have determined in step 2. We have these 8 electrons. So when you form the bond, we have 4 bonds formed, and each of these lines are as a result of 2 electrons. So 4 times 2, 8 electrons. We have used all the 8 electrons when writing the structure of this molecule. And then after that, we determine if the hydrogen has 2 electrons, because it has to follow the duet rule. We have to also determine if the carbon has octet of electron, because it follows the octet rule. So in this case, the hydrogen is surrounded by 2 electrons. Each of the hydrogens, because of the single bonds, 2 electrons around each of the hydrogens and 8 electrons around the carbon. As a result, this is a valid Lewis structure, adding 4 2-electron bonds around a carbon. It uses all the 8 valence electrons, so nothing is left. So we do not have any electrons to use as lone pair of electrons. So we will not have any electrons to form to put as a lone pair electrons. So the first, we use the electrons, which we determined in step 2. We use those electrons to form a bond. And then if you are left if you have any balance left, it is only when then you put this at the balance electron as a lone pair of electrons. Okay. So now, after you have drawn the Lewis structure of the molecule, you can cross-check whether the Lewis structure you have drawn is valid, whether the Lewis structure you have drawn is correct or not. If it is correct, the answer to these three questions, 1, 2, 3, must be yes. Have all the electrons been used? All the valence electrons been used? The answer to this must be yes. Is each hydrogen surrounded by 2 electrons? The answer to this also should be yes. Is each second row element surrounded by no more than electrons? The answer to this should also be yes. If the answer you have for these three questions is yes, the Lewis structure you have drawn is valid. In the case of methane, CH4, we had 8 valence electrons. And then when we formed the molecule of methane, we used all the 8 electrons. So the answer to question 1 is yes. Is each surrounded, is each hydrogen surrounded by 2 electrons? Of course, yes. Is each secondary row element, in this particular case, carbon, surrounded by no more than 8 electrons? The carbon is surrounded by 8 electrons. So the answer to these 3 questions is yes. Therefore, the structure we have drawn for methane is valid. It is a correct Lewis structure. So let me give you another example. Drawing the Lewis structure for methanol, a compound that has got molecular formula of CH4O, 1 carbon, 4 hydrogen, and 1 oxygen. So the first step is arrange the atoms. You should not forget. You have to do these things step by step. If you do it step by step, if you do it logically, you will not be lost. First, you arrange the atoms. So when you arrange the atoms, we have 4 hydrogens. Those 4 hydrogens will be on the outside. We have a carbon as a first approximation. We will not surround the carbon by more than 4 atoms. We have oxygen as a first approximation. Will not surround the oxygen by more than 2 atoms. So we arrange them like this. Hydrogen on the outside, 4 atoms around the carbon, 2 atoms around the oxygen. And then this is arrangement. Okay, as you can see, the 4 hydrogens are on the outside. Then when you look at the carbon, it's surrounded by 4 atoms. 1, 2, 3, 4. Then if you look at the oxygen, it's surrounded by 2. This is what we do first. Then after that, step 2, you count the total number of valence electrons. So we have 1 carbon, 4 hydrogen, and 1 oxygen. What is the valence electrons on the carbon, the hydrogen, and the oxygen? We add them up to determine the total valence electrons. So we have 4 hydrogens. So of course, we have 1 carbon, 1 carbon. Carbon has got 4 electrons, 1 times 4, 4 electrons. We have 1 oxygen. The valence electron on oxygen is 6. 1 times 6, 6. We have 4 hydrogens. 4 hydrogens. The valence electron is 1. 4 times 1, 4. The total number of valence electrons on the molecule of CH4O methanol is 14. Now, in the third step, we'll use these 14 electrons first to form a single bond between each of these elements. A single bond between this carbon, hydrogen, this carbon, hydrogen, this carbon, carbon, oxygen, oxygen, hydrogen. We do that first thing first. Add a bond between each of the atoms involved. Now, how many bonds have we formed? 1, 2, 3, 4, 5. We have formed 5 bonds. Each of these bonds are as a result of 2 electrons. Since we have formed 5 bonds, the total number of electrons we have used are 10. Only 10 of the 14 electrons are used. So we have 4 additional electrons remaining, which we need to put on these elements that are involved in chemical bonding in CH4O in methanol. When we do that, we'll put these lone pair of electrons on the atom that does not have octet of electrons, not on the atom that has octet of electron, on the atom that does not have octet of electron. Now, when you look at this molecule, if you look at the hydrogens, they have formed one bond. As a result of that, one bond on the hydrogens, we have 2 electrons. The duet rule is followed. If you look at the carbon has got 4 bonds. It has got octet of electrons. But if you look at the oxygen has formed only 2 bonds. No additional electrons are on the oxygen. Then as a result of these 2 bonds, the oxygen only has 4 electrons. It does not have octet of electrons. Now these additional 4 electrons, we'll use them as lone pair. So we have 4 electrons. We put these 4 electrons as 2 pairs, okay? As 2 lone pair of electrons on the oxygen. These electrons, they are not going to be involved in bonding. They are unshared electrons. They are non-bonding electrons, and then they will be put on the oxygen atom. So you do that. Now you have this. Now when you look at this, if you look at the oxygen, it has formed 2 bonds. As a result of those 2 bonds, you have 4 electrons, and then it has got 2 lone pair of electrons. As a result of those 2 lone pair of electrons, we have 4 electrons. So 4 plus 4, 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8 electrons on the oxygen. On the carbon, 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then if you look at the electrons that are involved in this molecule, you will see we have 5 single bonds, 5 times 2, 10 electrons, and then 2 lone pair of electrons, bringing a total of 4, 10 plus 4, 14. All the 14 electrons of all the 14 valence electrons of the 4 hydrogens, the 1 carbon and the oxygen, are used when this molecule is formed. So this is a valid Lewis structure. It will answer all the questions, all the 3 questions we have. I outlined, yes. So this molecule uses all the 14 electrons, giving every hydrogen atom 2 electrons. Every second row element, 8. In this case, the carbon and oxygen. Okay. Now let's look at another example. Drawing a Lewis structure for C2H4. So in C2H4, we have 2 carbons and 4 hydrogens. Now we'll arrange these atoms. When we arrange, we'll put the hydrogen on the outside. Okay. We'll put the hydrogen on the outside. So we have H, these 4 hydrogens on the outside, and then we have 2 carbons. Now, when you look at this, if you look at the carbon, remember what we said. When we arrange the atoms as a first approximation, we should not surround a particular element with no more than the number of bonds it usually forms. That's what, for example, if it is carbon, we should not surround it by more than 4. So in this particular case, if you look at this carbon, it is surrounded by the 2 hydrogens and this other carbon, only by 3 elements. So that assumption did not say the atom cannot be surrounded by less than the number of atoms, the number of bonds it usually form. Even if we want to surround the carbon by 4, we will not have the hydrogens, okay? We will not have the atoms required to do so. So as a result, it is possible an element can be surrounded by less than the number of bonds it usually forms. But you should not forget, even after this, that the octet rule must be followed. When you look at this, the carbon can form only 1, 2, 3 single bonds, okay? 3 single bonds bringing 6 electrons. So there must be additional electron to fulfill the octet of the carbon, as we shall see in a short while. So after you have determined this arrangement, you will count the total number of valence electrons, 2 carbons and 4 hydrogens, the total number of electrons being 12 electrons, okay? So we'll use these 12 electrons to form a bond between here and here, here and here, here and here, like that, okay? 1, 2, 3, 4, 5 bonds. 1, 2, 3, 4, 5 bonds. Now, after we have done this, how many of the 12 electrons did we use? We only used 10 of them. 1, 2, 3, 4, 5. 5 times 2, 10. We are left with 2 additional electrons. And then those additional electrons, we must add them as lone pair. Now you have to see this pair, not single. They come as a pair. Now we have 2 electrons that are left. Then those 2 electrons, we'll put them as a pair. So if you look at the carbon, the carbons, this carbon, as well as this carbon, they only have 3 bonds, 3 bonds. 3 times 2, 6 electrons. So none of these carbons have octet of electrons. So we can put this additional 2 electron as a lone pair. You can put it on this carbon or on the other carbon, does not matter. But all the same, put those electrons as a pair. So we decided to put it here. Now, when you look at this carbon, you see it has got 1, 2 as a result of the lone pair. 1, 2, 3, 4, 5, 6, 7, 8 electrons. However, this carbon has got only 1, 2, 3, 4, 5, 6 electrons only. It does not have octet of electron. We have used all the 12 electrons, but we have a situation where one of the atoms, in this particular case, this carbon, not having octet of electrons. We must have octet of electrons. Now what we do, rather than having this lone pair on the carbon as unshared, as non-bonding electrons, we can use these 2 electrons as bonding electrons, so that we use these 2 electrons to form a double bond between the 2 carbons. So rather than being unshared electrons, they become shared electron. Rather than being non-bonding electrons, they become bonding electrons. So we take these ones, these 2 electrons, and form a double bond, okay, like that. When you do that now, you see each of the atoms, each of the carbon will have octet of electrons. Each of them will have 4 bonds, because this carbon, as you can see, it has formed 1, 2 bonds as a result of the double bond, and then the 2 bonds with the hydrogen, so 4 bonds, each of them 4 bonds. This is a valid Lewis structure 4, C2H2, C2H4. Now let's look at another example. Drawing a Lewis structure for C2H2, where you have 2 carbons and 4 hydrogens. First, arrange the atoms. This is how the atoms are going to be arranged. Hydrogens on the outside. Okay. And then you count the valence electron. 2 carbons, 2 hydrogens, like that, total of 10 electrons. And then you use these 10 electrons to form a bond here, here, here. Okay, like this. Then when you do that, we've used 6 of the 12 electrons. No, 6 of the 10 electrons. So we have 4 electrons, which we have not used. Then those ones, we use them as a pair. Now, if you look at the carbons, both of them have got only 2 bonds. As a result of these 2 bonds, they only have 4 electrons. Their octet is not fulfilled. Now, we'll use this additional 4 electrons to fulfill the octet of this carbon. So the easiest way to do is to put all the 4 electrons on one of the carbons. At least one of the atom will have octet of electrons if you do that. It's possible you can put one pair here, another pair here, but you'll have both of them unhappy. Both of them still unstable because they only have 6. So you can use this lone pair of electrons, and then you can put them on one of the atoms, on one of the carbons. When you do that, at least one of the carbons will have 1, 2, 3, 4, 5, 6, 7, 8 electrons, octet of electrons. However, this one does not have, all the 10 electrons are used. This one does not have octet. Since we do not have any additional electrons left, the only thing we need, the only choice we are left with to have the octet of this carbon fulfilled is to use these lone pair of electrons as bonding electrons. Use these electrons to form a double bond, and we see if the carbon has, if each of the carbons have octet. If it does not, if they don't have, you form another bond. So you use this to form like that. When you look at this, you see this carbon has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. However, this one has got only 1, 2, 3, 4, 5, 6. This one does not have octet of electron. But we have this additional electron, this lone pair of electron, this unshared electron on this carbon. We can use it to form another bond, a triple bond, like that. Then this is a valid Lewis structure for acetylene, C2H2, as you can see, between the two carbons, we have a triple bond, 3 bonds, and then the 1 bond with hydrogen each. So as a result, each of them has formed 4 bonds. As a result of those 4 bonds, we have 8 electrons on each of them. Okay. So this is just after placing all electrons in bonds and lone pairs, use a lone pair to form a multiple bond if an atom does not have octet of electron. Change one lone pair into one new bond for each 2 electron needed to complete the octet. This is what I have discussed. Now, the examples we've discussed so far are for molecules that are neutral. We have CH4, which is a neutral molecule. We had methanol, CH3OH, which is a neutral molecule. We had C2H2, C2H4. All these were neutral molecules. They do not have any charges. Since they do not have any charges, all the atoms will have no charges. But it is possible you can have an organic molecule, a molecule that has charges. So the example discussed above are for neutral compounds. However, compounds can also be either positively or negatively charged, and we should be able to draw the structure of such compounds and then assign charges to individual atoms in that particular molecule. These are the steps we have learned so far. Let me allow you to unmute. Okay, so that we can have a discussion. So my message to you all is it's not my wish not to allow you to unmute. Okay, we should be in a position, you should at any point stop me and ask question. But if there is going to be a lot of disturbance, I'll be forced to do that. So I don't like to do that, and I hope from now on you will remain muted unless you have a question, so that we have a class where there is no disturbance. Okay. Now, so far we have learned how to write the Lewis structure of molecules. Then if you follow these steps and the basic concept we have discussed, you should be in a position to draw the Lewis structure of many molecules. Okay, majority of the molecules, with some guidance, you will be able to draw their Lewis structure. I've given you simple examples. I like giving simple examples so that you understand the concept, the bare concept, without complications. Once you have understood the concept, you can apply it to any complicated situation. So I'll give you assignments which are more complicated than this. Then you'll use these principles in drawing the layout structure of those. And then we'll have a tutorial class organized. Then during the tutorial class, we'll have a discussion on if you have any challenge in drawing the layout structure of those molecules. Now, we want to have a scenario of a molecule that is charged. And then how do we draw the Lewis structure of a molecule that has a charge? It could have a positive charge or a negative charge. How do we draw its structure? Of course, drawing the Lewis structure, you just follow the same rules, the same steps, the same basic concepts. Except this time, we have to determine the charges on each of the atoms so that we know what caused which particular atom in that molecule made this particular molecule to have a positive 1 charge, a positive 2, a -2, or a -3. Which are the atoms that contributed to the charge you see in that particular molecule, okay? So this one is called formal charge. So that's what we are going to discuss, okay? So the decision as to where to put the charge is made by calculating the formal charge on each atom in an ion, okay, or a molecule. And then formal charge is a charge as assigned to an individual atom in a Lewis structure. And then the formal charge is calculated using this simple mathematical formula, okay? I will not discuss the mathematical formula right now. Before I do that, I want you to understand this concept. And to understand this concept, I will use simple, basic day-to-day thing, what we do in our day-to-day life. Then after you have understood that, then you can see why, how to calculate formal charge, and also why a molecule becomes neutral, why a molecule is neutral or positively charged or negatively charged. And then we can apply that concept in determining formal charge, okay? So let me give you a scenario, okay, where you have 100 shilling, okay? You have mia moja. This 100 shilling you have is not in the form of cash, but in the form of M-Pesa, okay? In your M-Pesa account, you have 100 shilling, 100. And then you go to the supermarket to do some shopping. Then you pick things. Then you go to the cashier. The cashier punches and tells you the cost of the items you have picked is 100 shilling, okay? You went to shop with 100 shilling. The items you picked cost 100 shilling. You pay that 100 shilling. What will you be left with? Can you tell me? You can unmute and tell me. Hello? Is it very complicated?
No.
So how much money will be left with?
0.
0.
0
Yeah.
means neutral, okay? Neutral. Okay? So let's have another scenario. Let's have another scenario. You went with the same 100 shilling to a supermarket. And then you picked items. And then the items were found to cost 80 shillings. You had 100. The items cost only 80 shillings. How much money will you be left with?
20.
20. Positive, isn't it? Positive.
Yeah.
Okay? Isn't it? You will have a positive balance. Cindy?
Yeah.
Now, Let's have another scenario, a third scenario. You go to the supermarket with 100 shilling. You picked items. And then when the lady or the guy at the supermarket, the cashier punches and they find that the cost of the items you have picked is 120 shillings. You remember, we're using M-Pesa, okay, to pay for our goods. So the cost is 100, and then you decide to pay using your M-Pesa. When you try to transfer the 120 shillings to the cashier, M-Pesa will tell you you do not have that much balance, but you can Fuliza, isn't it?
Really?
You can Fuliza and pay 120, but Safaricom will not let you go, isn't it?
Yes.
That's a debt, isn't it?
Mhm.
You'll have, what kind of balance will have? You'll have a positive balance or a negative balance?
Negative 20.
A negative 20 balance, okay?
Negative balance.
This is very clear, isn't it? So in the first
Yeah.
example, you had 100, you used all the 100. You are left with nothing, neutral. In the second case, you had 100, you used 80. You have a balance of plus 20, positive. In the second case, you had 100, but you spent 120. If you have credit facility through Fuliza, you'll have minus balance. Okay, now relating these two atoms, I want you to listen. Relating these two atoms that are involved in chemical bonding, what the atoms have when forming a chemical bond, what the atoms use when forming a chemical bond, what the atoms use to shop with when forming a chemical bond are their valence electrons. Okay, that 100 shilling is like the valence electron the element has. Then each of the element will come their valence electron. Okay?
Yeah.
Come with their valence electron, and then they get involved in chemical bonding. Now, after they have formed this chemical bond, then you count the number of electrons which this particular atom has used when forming that chemical compound. Then if you see if it has used the same number of electrons, like the same number of electron as it is valence electron, the charge on that particular element will be 0. If it has got, for example, if it is carbon, carbon has got 4 electrons in its valence shell. Its valence shell is 4. When you look around the carbon, the number of electrons it has used to form that particular molecule, if it has used 4 of them, 4 minus 4, it will be 0. However, when you count the charge on that carbon, you find, when you count the number of electrons on that carbon, you find it has only formed 3. 4 minus 3, it is plus 1. If it has formed 5, 4 minus 5 will be plus minus 1. Okay?
Yeah.
So with that, let me give you an example. Okay? Let me give you an example of determining formal charge. Okay? Okay, so now let's look at this example of H3O plus. Okay, this is the hydronium ion. Please mute. You only unmute when you want to talk. Okay, please mute, because it just brings a lot of noise. Huh? Unfortunately, that's how it happens. So sorry. So when you look at this molecule of hydronium ion has a charge of +1. It is the structure for hydronium ion is this one, and the charge on this molecule is +1. That's the charge of the molecule. The charge of H3O plus, H3O is +1. Now, which atom contributed to this +1 charge? When you look at H3O plus, we have 3 hydrogens and 1 oxygen. Which is this element that contributed to this charge on the hydronium ion? To determine that, we have to first of all know what the valence electron of each of the atoms is, because that's what they use to shop with when they form a chemical bond. That's what they go with to form a bond with other elements, okay? So if you look at hydrogen has how many valence electrons? How many electrons in its valence shell? How many electrons are there in the valence shell of hydrogen?
1.
1. So this is what it has, the hydrogen, okay? It does not have 2, it does not have 3, it only has 1. It goes with this 1 electron to form a bond with the oxygen, okay? So now, when you look at hydrogen, each of these hydrogens, they are the same. They have formed a single bond with oxygen, They are identical, okay? Now, when you look at this hydrogen, how many electrons do you see around the hydrogen? How many electrons do you see around the hydrogen?
2.
2. But of these two electrons, which one belongs to the hydrogen? Is it
1.
all the 2 electrons or only one of them?
1.
1.
Because you know, covalent bond is formed as a result of sharing of electrons, okay? So in this chemical bond between the hydrogen and the oxygen, we have this single bond, which is as a result of sharing of 2 electrons. The electrons are contributed by each of the hydrogen and oxygen. So when you look at this chemical bond, the electrons that is contributed by the hydrogen in forming the single bond with the oxygen is only one of the electrons. So what you see around the hydrogen is 1 electron that belongs to the hydrogen. So the hydrogen had 1 electron, that's a valence shell. And then in the molecule of H3O plus, the number of electrons that belong to that hydrogen is 1. 1 minus 1 is 0. Okay? So the charges on each of the 3 hydrogens is 0. The hydrogens are neutral. Now let's look at the oxygen. Oxygen has got how many electrons in its valence shell?
6.
6. Now it has got 6. Now, when you look at this molecule of H3O plus, how many bonds has the oxygen formed? How many bonds has the oxygen formed?
3.
3 bonds, isn't it?
Yeah.
Because of these 3 bonds, we have a total of 6 electrons, isn't it?
Yeah.
But from these 6 bonding electrons, how many of them were contributed by the oxygen?
3.
Only 3 of them, okay? So, and then you have those 3 electrons. How about this lone pair of electrons? To which element do this lone pair of electrons belong?
Oxygen.
Oxygen.
So, as a result, the total number of electrons on the oxygen are 3 of them, which is used to form a covalent bond with the 3 hydrogens, and then these 2 electrons. So 3 plus 2, 5, okay? Isn't it?
Yeah. Yeah.
How many electrons were the valence? How many were the valence electrons of the oxygen?
6.
The valence electrons of the
6.
oxygen were 6.
6.
How many electrons did it use in forming this molecule? 5. 6 minus 5 is positive 1.
1.
So the charge on the oxygen when this molecule of H3O plus is formed is +1. The hydrogens were neutral. The charges on the hydrogens were neutral. Each of them were 0, 0, 0, the charges. So 0 plus 0 plus 0 plus 1 of the oxygen is +1. The +1 charge you see on H3O plus is as a result of the fact that the oxygen is positively charged. That the oxygen has got a +1 charge. Okay? Hello?
Yeah. Okay. Yeah.
Now, so what it is, like for example, when you went to the supermarket, you went with 100 shilling. Okay? And then money was being deducted from this 100 shillings to pay for the items you bought, isn't it? So now,
Yes.
for an atom, what it has to shop with is the valence electrons. Okay. Then from these valence electrons, what will be deducted is the number of lone pair of electrons on the atom. These ones, see, this lone pair of electrons belong to that element. Okay. The number of lone pair of electrons, and then half of the electrons it has used to form a bond with other elements, because it is only half of the electrons that belong to that particular element. That's why when this formula is derived, it's taken this into consideration. Formal charge on a particular element is the number of valence electrons. From that, we deduct minus the number of non-bonding electrons, the electrons that are not involved in bonding, like the two lone pair of electrons. I mean, the two electrons you see on the oxygen, those ones belong to the oxygen. So number of valence electrons minus bonding electrons plus half of the bonding electrons, because among the bonding electrons, it is only half of them that belong to that particular element. So from the number of valence electrons, you subtract the sum of the bonding electrons and half of the bonding electrons. When you do that, you'll have the formal charge on that particular element. Does it make sense? Hello? Does this formula make sense?
Yeah, it does.
Okay, good. Thank you so much. So now let's just apply, okay? Using this, let's calculate the formal charge on the hydrogen, for example, in this particular case. So to calculate the formal charge on the hydrogen, for hydrogen, the number of valence electrons is 1. Number of non-bonding electrons on the oxygen, see, do not see any non-bonding or unshared electrons on the hydrogen. So those are 0. And then the number of bonding electrons, the electrons that are involved in bonding, you have this single bond. As a result of this single bond, there are 2 electrons. Now, when you calculate the formal charge will be 1, which is the valence electron, minus the number of non-bonding electrons, 0, plus half of the bonding electrons, half of 2. So 1 minus 1, it will be 0. When you calculate for the oxygen, the valence electrons on the oxygen is 6. The number of non-bonding electrons on the oxygen are these ones, you see, 2 of them. And then the number of bonding electrons, as you can see, the oxygen has formed 3 bonds. So each of the bond is 2. 3 times 2, 6. So when you calculate the formal charge on the oxygen, from its valence electrons, 6, you subtract the number of non-bonding electrons, 2, plus half of the bonding electrons, half of 6. So 6 minus 2 plus 3, 6 minus 5, it is plus 1. So this is how we calculate formal charge for any element, okay, in any compound, okay? So the overall charge on the ion, the overall charge on the H3O plus in this case is the sum of the formal charges on each of the atoms. So we had 3 hydrogens. The charge on the 3 hydrogens was 0. We had 1 oxygen, its charge was plus 1. So 0 plus 0 plus 0 plus 1 is equal to plus 1. that +1 charge we see on the hydronium ion is because the oxygen is +1. Let me just tell you. So you can have +1 in many different ways. For example, you can have +1 because you have -2 + 3. -2 + 3 is basically 3 - 2 + 1, okay? You can have +1 because you have -1 and +2. So it is possible you can have a +1 because one of the element has a charge of -1, and then the other element has a charge of +2. -1 + 2 is +1. So that particular charge you see on a particular molecule is a sum of the charges on that particular molecule of the elements in that particular molecule. Okay, so you cannot say +1 is because one of the atom has a +1 charge. It does not necessarily come as a result of that fact. It is possible one of them has a -3 charge, the other one can have a +4. 4 - 3 + 1. Okay. So now this is a determination of formal charge on elements using calculation. Okay. By doing calculation, you can determine the formal charge on a particular element. But it is possible to determine the formal charge on an element without doing any calculation. Okay, please mute. Please mute. Hello, hello. Please mute. Annette. Annette, you have raised your hand. Yes, yes.
I have a question.
Please ask.
On your previous slide, I didn't understand the bonding electrons.
You know why? You know, Annette, listen. Okay.
Yeah.
When you form a bond, for example, between hydrogen and oxygen, okay?
Okay.
That covalent bond, hydrogen will contribute 1 electron, oxygen will contribute 1 electron, isn't it?
Yes.
So we have that bond between hydrogen and oxygen. So now you have these two electrons in the chemical bond, okay? That single bond, isn't it? Now,
yes.
in this single bond, we have 2 electrons. One of the electron is contributed by the hydrogen. The other electron is contributed by the oxygen. So if you are asked to determine, or if you are to determine how many of the electrons of this bond is contributed by the hydrogen, of course you will say it is 1. Yes. Isn't it true?
Yeah.
On the oxygen, it's also 1. But it's like the formula when you are calculating in the formula, that's why we put half of the bonding electrons, because it is only half of the electrons that are involved in the chemical bonding that belong to that particular element. Isn't it true?
Yes.
So like if you have oxygen, for example, in this H3O+, it has formed 3 single bonds. 3 single bonds. As a result of these 3 single bonds, there are 6 electrons, isn't it, that are involved in bonding. But it's only half of those that belong to the oxygen. That's why I put half times 6.
Okay.
Is it okay?
Yeah.
Yes. Thank you so much.
Thank you.
Excuse me, sir.
Yes.
Still on the previous slide. You also told us that oxygen has a tendency to form only 2 bonds, but this time it has formed 3 bonds with hydrogen.
Yes. So that means now, okay, that's why it will be related to what I'm going to discuss now, okay? So just wait a bit.
Okay,
Let me discuss this slide and so that your question will be answered, okay?
Okay, thank you.
Let's go to oxygen, okay? Let me start with what you have asked. If you look at oxygen, oxygen has got 6 electrons in its valence shell. Since it has got 6, in order to have 8, it needs additional 2 electrons, okay? Because 6 plus 2 is 8. That's why oxygen forms 2 bonds, okay? Oxygen, like in water, H2O, it forms 2 bonds. Also, so when you have oxygen, an element that forms two bonds. So if you see in a particular molecule, then you look at the oxygen, and then you see the oxygen in that particular form molecule has formed two bonds. When you see that, you will say the oxygen is neutral. Let's take even nitrogen, okay? Nitrogen. Nitrogen forms three bonds. So if you look at a molecule where the nitrogen has formed three bonds, without even doing any calculation, you will say the charge on the nitrogen is 0. But it is possible an element can form more than the number of bonds it usually forms. So if oxygen forms 2, if nitrogen forms 3, these are the number of bonds they usually form. Then their charge on those atoms will be 0. Okay? But it's possible oxygen, as in the case of hydronium ion, it forms 3. Oxygen, as in the case of sodium hydroxide, potassium hydroxide, minus OH, which you have learned in high school, isn't it? Where you have a bond between oxygen and hydrogen. Only one bond. It is possible. Oxygen can have 3 bonds. It is possible. Oxygen can have 2 bonds. It's all ammonia for nitrogen to have 4 bonds, because ammonium ion, NH4, where you have the nitrogen has formed 4 bonds. It is possible an element can form more than the number of bonds it usually forms. It can also form less than the number of bonds it usually forms. But when it forms more than the number of bonds it usually forms, it must be charged. It will be either positively charged or negatively charged. Okay, so when you have an element forming more than the number of bonds it usually forms, like nitrogen, if it forms 4 bonds, like oxygen, if it forms 3 bonds, it will be positively charged. But if an element forms less than the number of bonds it usually forms, nitrogen forms 3 bonds, but if it has only 2 bonds, like instead of ammonia, NH2, NH3, if you have NH2, where the nitrogen has formed only 2 bonds, in this case, the nitrogen will be negatively charged. It will have a -1 charge. If you look at oxygen, if oxygen forms only 1 bond, as in the case of hydroxide ion, HO minus HO, the charge on the oxygen will be negatively charged. Okay, the same will not apply to carbon. Carbon, it can form 3 bonds, okay, less than 4. It can be positive or negatively charged. Maybe this one I will discuss later, okay? But for now, I don't want to confuse you by bringing some other concept, okay? But if you have element other than carbonate, like nitrogen and oxygen, which are very important in organic molecules, if they form the same number of bonds which they usually form, they will be neutral. If they form more, they will become positive. If they form less, they will become negative. See, if you look at H3O plus, let me take you even to our example, okay? If you look at H3O plus, on the oxygen, how many lone pair of electrons do we have on the oxygen? 1 only, isn't it? Senior, only 1. But on the oxygen, we normally have 2 lone pair of electrons. So it has used its electron to form a bond with hydrogen. It has used its own electron to form a bond with hydrogen. So it has lost electron. So when something loses electron, it becomes positively charged. That's why the oxygen is positively charged. But in the case of HO minus, hydroxide, HO minus, on the oxygen, in the neutral oxygen, we have 2 lone pair of electrons. But in HO minus, where the oxygen forms only 1 bond, on the oxygen, we have 3 lone pair of electrons, additional pair of electrons. It has gained electrons. That's why it becomes negatively charged. Okay, so so to make it very simple, if you have an element, and then if this element has formed the number of bonds it usually forms to fulfill its octet, it becomes neutral. But if it forms more, it becomes positive. If it forms less, it becomes negative. Is it okay? Hello? I think it is clear. But all the
Yes,
same.
it's okay.
Okay, good. Now, as I finish, you remember what I said as step one when drawing the Lewis structure is to arrange atoms. Then, as I told you also, arranging atoms is not an easy thing. Because let me just give you a simple example. If you are asked to draw the Lewis structure of a molecule that has got 2 carbons, 6 hydrogens, and oxygen, C2H6O. These 2 carbons, 6 hydrogens, and 1 oxygen, they can be arranged in more than one way. You remember in high school, you learned about isomers. Huh? Isomers are chemical compounds that have the same molecular formula but different structure. For example, if you take C4H10, 4 carbons and 10 carbons, like the butanes. Those 4 carbons, they can be arranged in a line. You have normal butane, but you can have the 3 of them and then a branch in the middle to give us isobutane. So you can have normal butane or isobutane. Then if you increase the number of carbons, the number of possible ways in which they can be arranged becomes wild. Very many possibilities, okay? So it is possible that you can have an acceptable arrangement of atoms, a number of acceptable arrangement of atoms for a molecule with a particular molecular formula. For example, if you take C2H6O, in one case, it can be organized like an alcohol, ethanol, okay? It can be, in another way, it can be organized like an ether. But when you look at both of them are C2, we have 2 carbons, the 6 hydrogens, and the oxygen. 2 carbons, oxygen, and 6 hydrogens. There is no mistake at all on your part if you have drawn the Lewis structure for this molecule being this one or this one. There is no mistake at all. Based on the information you have, if you are a very good student, you will draw both structures, okay? So you can have isomers like this. The only way you can be certain about whether the structure is this one of the alcohol or the ether now, additional information. For example, you can do a test in the laboratory and you determine one of them, that's the molecular, you have a molecule that has got a molecular formula of C2H6O. And then you do some test with this molecule, which you don't know. All you know, it has got 2 carbons, 6 hydrogens, and 1 oxygen. Then you play around with it in the laboratory and you determine it to be an alcohol. Okay? So you have these possible structures, but since the experimental data you have indicates this molecule to be an alcohol, you will just say it is a 1. Okay? So when the number of carbons and hydrogens, blah, blah, increase, you remember even in high school, you learned that the molecular formula for glucose is C6H12O6, okay? These are called hexoses. I don't know, did you study about carbohydrates in biology or in biochemistry?
Yes, in biology.
Knowledge.
So what are the other examples of hexoses? You have mannose, isn't it? Galactose, glucose, etc., isn't it? Isn't it true?
Yeah, it is.
So all these, they have the same molecular formula of C6H12O6. But their arrangement is different. So, okay, unless you have additional information, as the number of carbon atoms increase, the number of possible structures of the arrangement of atoms increase. It is possible for those molecules to be arranged in many different ways. So I'm not saying that you should be frustrated by this, that you have this molecular formula, which you have determined experimentally, and then you want to know how these atoms are arranged. And then you'll be obtaining additional data from other experiments to help you narrow that the structure of the molecule is this one. For example, in this particular case, if you do an experiment for an alcohol and you determine now it is not, if it tells you it is not an alcohol, then the structure is that of the ether. If the experiment you conducted tells you it is an alcohol, the structure is this one. Okay? That's all. Now, from next week, we'll learn about exceptions to the octet rule. Exceptions to the octet rule. It is possible you can have a covalent molecule formed, and then when you count the number of electrons around a particular atom, it must have less than 8 electrons. Disobeying the octet rule. It's also possible that particular element might have more than 8 electrons. There are exceptions to the octet rule, and then we're going to discuss those exceptions with a reasonable explanation why they should have less or more. Kosovo? So do you have any question?
Yes, I have a question.